Here's an example of the mean value theorem. Given the function f of x equals x cubed in the interval -2 to 2, first, can the MVT be applied? And then if we answer yes, we can say why, and if we answer no, we can say why not. So we'd have to first determine whether these two conditions are met. Is x cubed continuous over the interval -2 to 2? Well, polynomial functions are always continuous over all real numbers. Yeah, this thing is continuous. And then if we consider whether f is differentiable, well, that's if the derivative exists everywhere, but the derivative of a polynomial function is yet another polynomial function. So not only is every polynomial continuous, every polynomial is also differentiable. So because of that, we can say yes, f of x is A, continuous on the interval -2 to 2, and B, differentiable on the open interval -2 to 2. Generally speaking, you don't have to go through the proof of those two statements. You just have to say explicitly that those two requirements are met. And because we get a yes here, we have to find all such values of c that satisfy the mean value theorem. In other words, find all values of c such that f prime of c equals f of b minus f of a over b minus a. Find the places where the I rock equals the a rock. The instantaneous rate of change equals the average rate of change. Remember, the I rock would be the slope of the tangent line. That's not how you spell tangent. Tangent line, and the average rate of change is the slope of the secant line. So have those pictures in your mind of the graph, because that can sometimes help us understand what's going on a little bit better. Anyway, so f of x equals x cubed, f prime of x equals 3x squared. So the f prime of c equals f of b minus f of a over b minus a. We're going to try to solve for c in that equation. We are going to put -2 in for a and +2 in for b, and we get f of 2 minus f of -2 over 2 minus -2, which is 8 minus -8. Over 2 minus -2, or 16 over 4, which is equal to 4. So we need to figure out when is the derivative equal to 4. Well, the derivative is 3x squared. F prime of c is 3c squared. So we'll just bring that down. And then we'll solve for c. We'll divide by 3. We'll take the square root, and then we'll get, in this case, 2 answers, and then we ask the question, are both of these in the interval? And since they both are, we would go ahead and say both of those are answers. And I would encourage you to graph this and explore the slopes of the tangent lines and the slopes of the secant lines. Actually go ahead and figure out those equations and graph them. That's really going to solidify your understanding of these things. So on the last theorem, the mean value theorem, we saw that the endpoints weren't at the same level. F of a doesn't necessarily equal f of b. We have an extra requirement that we could enforce, namely that f of a equals f of b. So we're starting and stopping at the same horizontal height. Horizontal height? Vertical height, right? The same y value. That's not a requirement for the mean value theorem. It's just an extra thing that could happen. And we actually call this thing Rolle's theorem. I think historically Rolle came along and figured out this theorem before the mean value theorem, which is a more general theorem. So Rolle's theorem is a special case situation of the mean value theorem. But other than that, it's exactly the same. If you take a look at what's going on here, we have the same original two requirements. F is continuous over the closed interval, and F is differentiable over the open interval. And we have this third requirement that the y values of the endpoints are the same. Well, this is the same theorem. This is still the mean value theorem, but let's think about what the average rate of change is. What is the AROC? The AROC is f of b minus f of a over b minus a. But if f of b equals f of a, then we've got a value minus itself. It's 0 over b minus a, which is equal to 0. So we can see that graphically because of the horizontal tangent line. So all we're saying here is that there will be some point somewhere along the way where we have a horizontal tangent line between the starting point and the ending point, guaranteed by Rolle's theorem. And again, this is just the mean value theorem with that extra piece that the two endpoints have the same y value. These are three requirements. We need to know those. So if we take a look at this example, can Rolle's theorem be applied? Well, probably. It's a polynomial function, so it's going to fit the first two requirements. So let's just take a look at the two endpoints. F of 0 equals 0 squared times 0 minus 1, which equals 0. And f of 1 equals 1 squared times 1 minus 1, which is also 0. So yes, because, semicolon, A, because f of x is continuous on the closed interval 0 to 1. B, f of x is differentiable on the open interval 0 to 1. And finally, C, f of 0 equals f of 1. We do have to show this step right here. We do have to show that they're equal. So because of yes, we're going to find all values of C such that that satisfy Rolle's theorem. In other words, find all values of C where the AROC equals the IROC. All right, so we know that f of x equals x squared times x minus 1. I don't really feel like doing the product rule, so let's distribute and get x cubed minus x squared. That's going to give us an f prime of x value of 3x squared minus 2x. And now we're going to go ahead and try to set the f prime of c equal to f of b minus f of a over b minus a. We already know equals 0, so we're just going to put 0 here. So that's just going to be 3x squared minus 2x equals 0. So we'll solve for x. We can factor out an x, and we'll end up with x equals 0 and x equals 2/3 as two values. Now, do we pick both of these? Well, no. We don't pick this one because, not that it's incorrect that x equals 0, but x equals 0 is not in the interval. So we're only interested in values between 0 and 1. 2/3 is in between 0 and 1. So this would be our c value. I often do this. I accidentally change my c's back to x's. I probably should have put a c here instead. Doesn't really make much difference. C is a particular x value.